I won't have access to the recording, and actually, I think our cloud ilija. So recording to the cloud was disabled. So anyone who might be wanting to do a recording, you can make a request, I'll allow. So that you can record to your device. So 0.1 multiplied by 30 plus 0.4 multiplied by. Now, the person who has made a request for recording, where does it record?
On my PC.
Okay, so anyone else also who needs to do that can do a request. So 0.1 multiplied by 30 plus 0.4 multiplied by 70 plus 0.3 multiplied by 100, then plus 0.2 multiplied by 150. And this should be giving you 91. Also the same, negative this multiplied by 0.1, this and this, this and this, this and this as a sum should be giving you 162. And since we are talking about profits here, the EMV should be picking the maximum. Therefore, EMV, of course, will pick option number B, regardless of this high variability that we have here. So EMV will still go for the second action on the stock number B. So it will make a decision on investing in stock B because that is the one which is giving us the highest expected monetary value. Now, when you go to the risk to ratio case, what are we doing is that we need to get the variance. So the EMV for A, which is 91, the variance is given by, so get the variance for this. To be given by, this is the formula for computing variance. So we know, of course, that to compute the variance, you need to get each and every observation minus the mean. And we say that getting the expected value is the same as getting the mean in statistics. So these EMV values that you're getting, will take them to be our means. So I take each and every observation minus the mean, and I square that. And I multiply by the probabilities. So taking this to be a case of maybe a discrete kind of probabilistic discrete kind of a table in nature. So I'm taking the Vij, which is, for example, now at 30 here, minus the mean, which is 91, which is giving me a negative 61, and I multiply by the corresponding probability, 0.1. The second one, I'm taking 70 minus 91. So 70, this is 70 minus 91, which is giving me negative, which is giving me negative 21. This here is again the 100 minus 91, which is giving me a 9. And this one here is the 150 minus 91, which is giving me a 59. And this is multiplied by the corresponding probability. But remember, we are still again squaring it. So of course, because of the square deviations, there is no point where you get our variance to be a negative. It's always a positive. The variability will always be a positive value. So if you check this, it is giving us a 1269, which is variance. Then getting the square root. So this sigma A is the square root of 1269, which is now giving us this particular value to be the standard deviation for the stock. That is for the first state of nature, not the first state of nature, but the first alternative, that is taking on stock A. The variance for stock B again has been computed in the same way. So taking each and every observation minus the expected value, which is 162. So we take the expected value here Vij negative 50 minus 162, giving us this higher value. So this is negative 50 minus 162. This is the second one, 30 minus 162. This is the third one, 250 minus 162. And this is the fourth one, which is 400 minus 162. And all these values are squared and multiplied by the corresponding probabilities. We get this to be our variance. This is sigma squared. Then now sigma value for the B1 is being taken to be the square root of 25,116. And we are getting this particular value here. Now, what we are saying that we note below is that the EMVA is equals to the mean of A, which is supposed to be equals the summation of Vij multiplied by the probabilities. This is how we are getting the expected monetary value, and this is something that we have discussed before or earlier. Then now the variance, we are getting the variance based on these particular formulas, whereby we are getting the summation of the deviations from the expected monetary value for each and every decision that we take. For example, here we have two decisions or two decision alternatives. They're either to pick on stock A or to pick on stock B. We subtract the mean of that is the expected monetary value, the deviations of the from the expected monetary value for each and every payoff that we have, each and every decision. We square that and we multiply by the corresponding probability to get the variance. Now, once we have the variances, as they are shown, right? So once you have the variances, we are saying that because you are comparing two stocks with different means, you should evaluate the relative risk associated with each and every stock. So once you have computed the standard deviation and the return to risk, you compute what you call the coefficient of variation. Now, there are this star 2100 that is being mentioned. Of course, should be your introduction to probability for this particular case. I don't know whether yours should be 2101, VSTA 2101. I'm not sure whether it is 2101, something. 2101, that is probability and statistics 1. So from probability and statistics 1, you're told out to, there was a computation of coefficient of variation, whereby you take the sigma, we normally take the standard deviation and divide that by the mean, and you multiply that by 100. So this coefficient of variation here, we are taking for each and every action. So the computed standard deviation, each and every action divided by the expected monetary value. So if you take the computed standard deviation for the first one, it is 3562. And for the second one, 35.62. And for the second one, it is 158.48. So I take 35.62 divided by the mean, which was 91. That is whatever we have been using for the EMVA, multiplied by 100. I get 39.1. For the second one, 158.48 divided by 162 multiplied by 100, I get 97.8. Therefore, for this, we can see that there is a much variation in the return for stock B than for stock A. And when there are large differences in the amount of variability in the different events, the criterion under the EMV or the EOL needs to express the relationship between the return as expressed by the EMV and the risk as expressed by the standard deviation. Therefore, this equation now that we are defining here is going to be giving us the return to risk ratio as the expected monetary value of action A divided by the standard deviation of an action I. So the return to risk ratio is the same as the EMV A divided by sigma or the standard deviation of AI. So the return to risk ratio selects the course of action with the largest RTRR. And for each of the two stocks that we have discussed previously, the return to risk ratio is given as 91 divided by 35.62, which was the standard deviation, which is given 2.55. Then this other one is 162 divided by 158.48, which is given as 1.02. Now, picking the largest, the one with the largest RTRR, or the return to risk ratio, we are picking alternative. So alternative A. And thus we are seeing that relative to risk as expressed by the standard deviation, the expected return is much higher for stock A than for stock B. So stock A has a smaller expected monetary value than stock B, but also has a much smaller risk than stock B. Therefore, using the risk or the return to risk ratio, stock A or investing in stock A will be the best alternative as compared to investing in stock B. So first here, what you are doing is that we are trying to establish whether there is a variation or the amount of variation that we have for each and every stock. And this was enabled by first computing the standard deviation, then obtaining the correlation coefficient or the coefficient of variation. So you can see from the coefficient of variation here, stock B is more varied as compared to stock A. Then, since we have that variation from the coefficient of, since we have these variations from for the two stocks, then we now compute the return to risk ratios. And based on the return to risk ratios, you can see that actually we are opting for alternative A, which is giving us a higher value of the return to risk ratio, meaning that from alternative A, we could expect more returns, or the risk that we can get by investing in alternative A is low as compared to alternative B. So therefore, the return to risk ratio alternative based on the return to risk ratio, alternative A is more preferred as compared to alternative B. So we have again some exercise questions here, which is asking you to get the EM, the EOL, and there should be several of them. So there are several questions, I think up to the last part. So try as many as possible, and I'm going to check on this and highlight some to form part of the assignment that we are going to give. So I'll select some of the questions that we have here, and we form an assignment out of this. And of course, the way the questions are structured here is the same way we expect our exam to be structured in terms of the decision theory part. So that concludes, or that ends the decision theory part of the unit, so that I look at something on the last part, or on the Bayesian. And of course, the Bayesian, I'll try to maybe discuss that in regard to a decision theory again. No, Simbwa is asking for notes. Simbwa, this is the same document that I shared with you through the class group.
Okay.
Maybe let me just resend it. I have shared it. It's just the same one that I've been using all along. Already you had this. Maybe the second one now that I want to move to. Unless with a question, allow me to move to the Bayesian. Anyone with a question? Anyone with a question? Okay. If you have no question, then I think we will proceed. So let me move to the second part. That is a Bayesian estimation and inference. Second part, Bayesian estimation and inference. Now, Bayesian estimation is a different way of looking at statistical methods. So whatever you normally cover in most of the cases, it's about the frequentist approach, or what you call the classical methods. And normally that we have fixed constants for some defined probabilities, or some probabilities that are defined. But for Bayesian normally it's computing some posterior probability based on some prior known information and a likelihood function. So we get a likelihood function and some prior probability. Then out of that, we get what you call the posterior distribution. So we are saying that here, the most frequently used statistical methods are known as the frequentists, or the classical methods. And these methods assume unknown parameters and fixed constants. And they define probability by using the limiting relative frequencies. So it follows also the assumption that probabilities are objective, and you cannot make probabilistic statements about the parameters because they are fixed. So Bayesian methods is offering a different alternative, whereby it is supposed to treat these particular parameters as random variables and define the probability as the degree of belief. That is, the probability that an event, the probability of an event is the degree to which you believe the event is true. So it follows from postulates that probabilities are subjective and they can make probability statements about parameters. Therefore, the term Bayesian comes from prevalent Bayes theorem that gives us the probability of a particular action happening, given that we have another activity or another thing has already happened. So it is normally some sort of conditional kind of probability, which is telling us that we are finding the probability of maybe event A occurring, given that event B has already occurred, which is normally the probability of the A union B divided by the probability of action A. Sorry, not A, but probability of A. So this is normally giving us the Bayes theorem. So you're going to look at the Bayes theorem and even try to see how this can be proved. Moving on here to disable theta. Yes. Now we are seeing that as opposed to point estimators, which are the mean variances that are used in classical statistics, whatever is used in Bayesian statistics, it is concerned with generating the posterior distribution of unknown parameters, given both the data and some prior density of these parameters. As such, Bayesian statistics provides a much more complete picture of the certainty in the estimation of the unknown parameters, and especially after the confounding effects of the nuisance parameters are removed. So suppose we are interested in doing an estimation of a parameter theta. So we're estimating some parameter theta from some given data y. So it is a y vector, meaning it is composed of y1, y2 to yn observations by using a statistical model that is defined to be probability, the probability density, that is the y given theta. Bayesian philosophy is supposed to say that theta cannot be determined exactly, and uncertainty about the parameter is expressed through the probability statements and distributions. So you can say that theta is going to be following a normal distribution with mean 0 and variance 1. If it is believed that that this distribution best describes the uncertainty associated with the parameter that we have here. So therefore, we need to have some prior probability so that you'll be able to estimate the parameters of the new density that you're coming up with. Now, we are saying that the following steps describes the essential elements of Bayesian inference. Step number 1 is that the probability distribution for theta should be formulated as pi theta, which is known as the prior distribution, or just the prior. The prior distribution expresses the beliefs about the parameter before observing the data. So we need to have some prior belief about the parameter, meaning that we are believing that our particular parameter is maybe normally distributed, or has a binomial distribution, has a Bernoulli distribution, or has a gamma distribution, all those kinds of distribution. We have a prior belief about the parameter theta, and this is giving us the prior distribution. Then given observed data values now, y1, y2, so given some data values, we can choose a statistical model given by the probability of y given theta to describe the distribution of the given theta. Then out of that now, we update our belief about theta by combining information from the prior distribution and the data through calculation of what we now refer to as the posterior distribution. And the posterior distribution is now this pi theta given the data. So the distribution, so we are updating the distribution of our new parameter theta given the data values. So, and it is now based on this particular statistical model that you obtain from the data given the parameter theta. We get this. So normally we will say that the pi theta given y should be directly proportional to getting the p of y given theta multiplied by the prior distribution, that is the pi theta. Or normally we take the prior distribution multiplied by this new statistical model, or the model of the data given the parameter theta, and this gives us the posterior distribution. So it involves three things. One, the prior distribution. Secondly, is the statistical model that you get from the observed data given the parameter theta. And then the third one, now a combination of the prior distribution and the data, you get the posterior distribution. So that is what forms the Bayesian. Moving on to some theory here regarding Bayesian statistics. So what is the origin of Bayesian statistics? It is said that they originate from the Bayes and the Laplace, that is in the late 1700s and 1800s to the mid 1800s. And in the early 1920s, someone called Fisher put forward an opposing viewpoint that statistical inference must be based entirely on probabilities with direct experimental interpretations. That is a repeated sampling principle. And in 1913, someone called, or in the Jeffreys book, which even there's a Jeffreys principle also in Bayesian, says that the theory of probability stated a resurgence of interest in Bayesian inference. And this continued through 1950 to 60, especially as problems with the frequentist approach started to emerge. The development of simulation-based inference has transformed Bayesian statistics in the late 20 to 30 years, or in the last 20 to 30 years, and is now playing a prominent part in modern statistics. So people are even trying now to adopt on the Bayesian techniques as opposed to whatever you have as the classical techniques that we have, because this is based on experimentation. Because basically you have some sample data and you have some prior knowledge about the distribution of a particular parameter. You're combining that to get an updated probability distribution called the posterior distribution. So what is the problem with frequentist inference, or the frequentist, the classical techniques that we have? So one thing about the classical techniques is that you're saying that the frequentist of inference, it does not contain the observed data. So the data is missing. So a confidence interval is a set of value function, C of x, that is contained. So this value function, C of x, is contained in this particular value there called the parameter space of the data x, which covers the parameter theta. And this parameter theta is taken to be, this is a denotation of subset, a subset of this particular function. And a function 1 minus alpha of repeated draws of x taken under the null hypothesis H0. So this is not the same as the statement that given data x is equals to x, the interval C of x covers theta probability 1 minus alpha, but it is a type of statement that we might wish to make. So what happens that in that the confidence interval, it's taken to be some set valued function, which is a subset of a parameter space of the data x and covers the parameter theta, which is which is contained in the set valued function here. So as an example, we are looking at, suppose x1, x2 are uniformly distributed with this and this, so that x1 and x2 are ordered statistics. Then the C of x will be equals to, this is now the function, it will be in the interval. Now this is a ceiling function where it is in the interval x1 to x2, and is alpha is equals to, I have the level of the confidence interval for theta. Now suppose the data x is equals to x, x2 minus x1 should be greater than a half. And this happens in an eighth of the data sets. Then theta within this parameter space is within this parameter space with a probability of 1. So this is now bringing in something else that is referred to as the order statistics, and that is what is considering this observation x1 and x2. But we are considering a uniform distribution with this particular interval. So the interval theta minus half, theta plus half, meaning the deviation is half from the actual midpoint here. So that is why alpha should be half the level of the confidence interval for theta. So we have here. Number 2. So these are just some theoretical things regarding the frequentist approach. So number 2 is that the frequentist approach depends on data that were not observed. So the likelihood principle says that suppose that two experiments relating to theta, E1 and E2, give rise to data Y1 and Y2, say that the corresponding likelihoods are proportional. That is, for all theta, the likelihood of theta Y1 E1 is equals to the likelihood of theta Y2 and E2. Then the two experiments leads to identical conclusions about theta. So the key point is that the maximum likelihood estimates respects the likelihood principle, i.e. MLEs for theta are identical in both experiments, but the significant tests do not respect the likelihood principle. So considering a pure test for significance, where we specify just the null hypothesis, we must choose a test statistics, Tx, and define the p-value for the Tx to be equal to T. That is a p-value of the test statistic that is at least as extreme as the probability that the probability of the test to be at least as extreme as whatever we have in the indicated in the null hypothesis. So the choice of Tx must amount to the statement about direction of likely departures from the null, which requires some considerations of alternative methods. So there are two cases here why we do not use the frequencies approach. It's one that the frequencies inference generally does not contain the observed data, and the frequencies inference depends on data which was not observed. So it does not have observed data, and it is relying, or it is basing its inference on some data which was not observed. So the calculation of p-value involves the sum or the integral. Now, normally, this is just the probability under the curve so that you get the p-value for each and every test that is, whether it is a t-test, it is a normal distribution and such. And the p-value is not the same as the probability that h naught given tx is equals to t. Now, defining the Bayes theorem before Bayesian, because this is what is actually the Bayesian is involved, or is it's based on this. So the Bayes theorem, from the definition of a conditional probability, it's saying that suppose we have we observe a random variable x, and we wish to make inference about another random variable theta, where theta is drawn from some distribution P of theta. From the definition of conditional probability, the probability of theta given x should be equals to the probability of x theta, that is all the observations there, divided by the probability of the first one, which is x. And this probability of x theta is the same as the probability of theta multiplied by the probability of x given theta. So we are saying that the conditional probability, we can express the joint probability by conditioning on theta. So the probability of x theta is equal to the probability of theta multiplied by the probability of x given theta. And then now putting these together gets the Bayes theorem, as the probability of theta given x should be equal to the probability of theta multiplied by the probability of x given theta divided by the probability of x. So with several outcomes, theta 1, theta 2, theta n, we have the probability of theta I given x to be equal to the probability of theta I multiplied by the probability of x given theta I divided by the probability of x. And here the probability of x is the same as taking the summation of the probability of theta I multiplied by the probability of x given theta I. And the probability of theta that we are talking about here, or the theta I, gives us the prior distribution for theta. So that is some known distribution. Then this other part here that we are computing here gives us the posterior distribution. And of course, this is equals to, we'll now be using the direct proportionality. We'll be saying that the posterior distribution is directly proportional to the prior distribution multiplied by the probability of x given the theta part there. Given the probability of x given the theta, that is the probability of the data given the theta value. Let's see an example on how Bayes theorem can be applied. So we are saying that at a certain assembly plant, 3 machines make 30%, 45%, and 25% respectively of the products. It is known that from past experience that 2%, 3%, and 2% of the products by each machine respectively are defective. Now, suppose that a finished product is randomly selected. What is the probability that this particular product is defective? So what is the probability of it being defective? So if a product was chosen randomly and found to be defective, what is the probability that it was made by machine 3? So first we need to look at these statements that we have here. The product is defective, and BI, that is the product, is made by machine 1, 2, or 3. So we apply the additive and multiplicative rules so that we have that the probability of A should be equals to the probability of B1 multiplied by the probability of A given B1 plus the probability of B2 multiplied by the probability of A given B2 plus the probability of B3 multiplied by the probability of A given B3. And you'll see that the probability of B1, which is 0.3, that is, we need that it is a defective. We need that it is defective and it is from what is the probability that it is defective and it is from any of these B1, B2, and B3. So 0.3 multiplied by 0.02, which is giving us the probability that it is A is now telling us that it is defective. So the probability that it is defective given that it is B1 is 0.03 and B1 is machine 1. So the probability that it is machine 1 is 0.3 and the probability that it is defective and it is machine 1 is 0.02 plus 0.45, which is the probability that it is machine 2, given that it is defective, it is 0.03 plus the probability that is machine 3, which is 0.25, given that it is defective 0.02. And we sum up that and we get this particular probability 0.0245. Then for the second one, we need now some condition that if a product was chosen randomly and found to be defective, what is the probability that it was made by machine 3? Now, choosing it randomly, using Bayes' theorem, we need that the probability that it is from machine 3 and it was defective. A is denoting whether it is defective or not defective. So A is a case of the probability that it is defective. Now, probability of B3 given A using Bayes' theorem should be written as the probability of B3 multiplied by the probability of A given B3 divided by the probability of A. The probability of B3, or the probability that it is machine 3, is given to be equals to 0.25. So probability that it is machine 3. So this here should be equivalent to the probability that it is from machine 3, which is 0.25, multiplied by the probability that it is defective and it is from machine 3, which is 0.02. And we multiply this. And not only multiply this, we divide this by the probability that it is from machine A. So the probability, no, not from machine A, the probability that it is defective, and the probability that it is defective is given by this earlier computed probability, 0.0245. So we have calculated the probability that it is defective, irrespective of which machine it is coming from. Then now the probability that it is from machine 3 and it is defective is now whatever is going to give us the 0.2041 that we have here. So that is how you could apply the Bayes principle to do computations of probabilities. Also, we have another example here, which is given two classifications. I'll leave you to look at that on your own, because we need the probability that we're having suppose that we observe the family has 5 boys and 5 girls and no boys. What is the probability that this family is a sex bias, meaning it has only girls? So the probability that there are no or we have one boy, given that all the rest are girls. Model-based inference, model-based Bayesian inference. Now I'm now including, it's still the Bayesian principle that we have defined here, but I'm now generalizing this to a particular parameter space. So I'm not talking about only one theta value. The parameter space will contain different parameters that can be defined for any given distribution. For example, the normal distribution, we talk of the normal distribution having 2 parameters, the mean and the standard deviation. When you talk about maybe the binomial distribution, we say that it has a binomial distribution with the parameter theta and maybe n number of observations and such. So for each and every distribution that we'll have to define some parameter space for it. So we are now getting the posterior distribution to be given by the probability that you have a particular parameter space given the observed data to be given by the probability for observed data given the parameter multiplied by the prior distribution that we divide by the probability of that particular data, where P of y, we are saying that you're discussing here below, the pi theta is the set of prior distributions of the parameter set theta. And before y is observed, the probability of this Fy given theta is the likelihood. So this, whatever you have as y, the observed data given the parameter is going to be the likelihood of y under the model. And then now we have the pi theta given, pi parameter space given y is now what you call the joint distribution for all the parameters we have. So sometimes it's called the full posterior distribution of a parameter set theta that express uncertainty about some parameter set. And this parameter set here is or parameter space is given theta 1 or is holding theta 1, theta 2, all the way to theta n. Now the denominator P of y, it is the integral over all the values of the parameter space of the product Fy given theta multiplied by pi theta, i.e. the Py or the probability of y is the integral across all the parameter space Fy theta multiplied by theta pi parameter space with respect to the parameter space, and can be regarded as a normalizing constant whose presence ensures that our posterior distribution is a proper density and integrates to 1. So by replacing this pi of theta with a constant, which is with a c, which is in short a constant of proportionality, then the model-based formulation of the Bayes theorem now converts or changes to. So we take that to be a normalizing constant. We could have that the posterior distribution is equals to 1 over c multiplied by Fy given theta multiplied by the prior. So this is the likelihood multiplied by the prior distribution. So by removing the constant from the equation, means one can express the Bayes theorem using now the proportionality sign here. So we are saying here that the posterior distribution is proportional to the likelihood multiplied by the prior. So the posterior distribution is directly proportional to the likelihood multiplied by the prior. So in most instances, for us to be able to compute the posterior distribution, we'll be finding the likelihood function and we multiply by the prior distribution. So the first thing will normally to find the likelihood function for any particular distribution given, then now we compute the posterior out of that, or you multiply that by the prior so that you can get the posterior. So moving on. So we are saying here, this is the parameter space that is being defined on this part here. That a nuisance parameter, the parameter that is a parameter that exists in the joint distribution of the model, though it is not a parameter of interest. The marginal posterior distribution of theta or of an empty or a subvector of interest, that is the parameter of interest, can simply be written as this pi of that subvector of interest given theta is the integral across this given parameter space, or these other space here. That is the parameter that we are not interested in, and having a combination of the two given y with regard to whatever we are not interested in. In model-based Bayesian, Bayes' theorem is used to estimate the anomalized joint distribution. Finally, the user can access and make inference from marginal posterior distribution. So under this model-based, the thing that you need to pick out of this is that the Bayes' theorem finally gets to this particular point whereby we are getting the posterior distribution by taking the likelihood multiplied by the prior distribution. So meaning in any instant, I'll need to get my likelihood and I need to get my prior distribution. I multiply the two functions to get the posterior distribution out of that. So what is a likelihood function? Or how do we obtain a likelihood function? The likelihood function expressed as L theta given X is a function of theta that shows how likely our various parameter values have produced the data X that were observed. In classical statistics, the specific value of theta that maximizes L theta given X is the maximum likelihood estimator of theta. In many common probability models, when the sample size n is large, the likelihood function is unimodeled in theta, meaning it has one maximum point. A definition talking about these observations, x1, x2, x3 to have a joint distribution, f x1, x2, x3 given theta. Given x1 is equals to x1, x2 is equals to x2, xn is equals to xn is observed, then the function of theta defined by the likelihood function of theta given x will be the same as the likelihood of theta given all these observations, x1, x2 to xn, which is equals to the function fx1, x2, xn given theta. And mathematically, x1, x2, and x3 are IIT, that is independently and identically distributed, as xi's to have this particular distribution, the fxi given theta. And therefore, the likelihood function L theta given x will be the product sum from I is equals to 1 to n of fxi given theta, where x1, x2, x3 to xn are the observed data values. So that is the data vector. So using the principle or the likelihood principle or of Birnbaum states that all the evidence about theta is contained in the likelihood function, and it is more convenient to use log likelihood. So normally the L theta, now not a capital, this L theta given x, a small L theta given x is normally the likelihood of the natural logarithm, that is the log of so when you talk about the log likelihood, we are getting the natural logarithm of L theta given x. And the definition almost seems to be defining the likelihood function to be the same as the PDF or PMF. And the only distinction between these two functions is which variable is considered fixed and which is varied. So when we consider the PDF for PMF fx given theta, we are considering theta as a fixed and x as a variable. And when we consider the likelihood function L theta given x, we are considering x to be the observed sample point and theta to be the varying of all possible parameters. So essentially, how we are going to be obtaining the likelihood function will be getting the product sum across the I is equals to 1 to n of fxi given theta. So we'll be given some particular distribution and we'll get the product sum from I is equals to 1 to n. Then we'll get the log likelihood function by taking the natural logarithm of the likelihood function. So that is about the likelihood function. On the way or before we end, we'll be looking at some cases on how we actually obtained or get the posterior distribution based on a likelihood and a prior distribution. So remarks is that the likelihood function is not a probability density function. And it is also important to, it is an important component of both frequentist and the Bayesian analysis. And it measures the support provided by the data for each possible value of the parameter. So by saying it is not a PDF, meaning that if you find the integral of the likelihood function from a particular point 0 to a particular point within a particular interval, you might not get 1 for that. If we compare the likelihood function at a 2 parameter points and find the L theta 1 given x to be greater than L theta 2 given x, then the sample we actually observed is more likely to have occurred if theta is equal to theta 1 than if theta is equal to theta 2. So that is if you have 2 or more than 2 parameters, which is now interpreted as saying that theta 1 is more plausible value of the true value of theta than theta 2. So we carefully use the word plausible rather than probable because we think of theta to be a fixed value. These are an example of getting the log likelihood or the likelihood function for that particular matter. One, or example one, is based on the normal distribution. So let me see whether, so that I don't get to too much detail, I'll leave the part, I'll stop at the part where we have the Bayesian framework so that I may continue from there in the next class physically as we write that. So let me just discuss these distribution with mean mu, variance sigma squared, where both mean and sigma squared are unknown parameters. The mean is within the range of real numbers, and sigma squared is greater than 0, meaning the variance is positive. With theta, so now our theta will be composed of 2 parameters, the mean and the sigma squared. So the likelihood is supposed to be given by getting the product sum from I is equals to 1 to n of our probability distribution. So if you check the probability distribution, fx, at the probability distribution, the fx given theta of the normal distribution should be given by 1 over 2 pi sigma squared, for example, multiplied by the exponential value of negative 1 over 2 into xi minus mu divided by sigma, and all this is squared. Or you could have this as negative 1 over 2 sigma squared, xi minus mu divided by sigma squared. Now what we are doing is that we are getting the product sum of this particular case from I is equals to 1 to n. So when I get the product sum of that, this is a constant. So if you are summing a constant n times, it will be raised to power n. So it will be 1 over 2 pi sigma squared. The whole of this is raised to power n. But since I've written I've written this all to in the numerator, that is why it is raised to power negative 1 over 2. it will be the square root of this. But I have the square root of 2 pi, 1 over the square root of that. So we are raising this to power n, which is the same as raising to power negative n over 2, because writing the square root as raised to power a half is what is bringing us to this particular point. Then the exponential value of 1 over 2 sigma squared has been factored out, so that I sum, because it is the product sum, so I sum over the observations, the xi minus mu, and we square that. Then, after obtaining this product sum, we get the log likelihood out of that. So this basically has given us the likelihood function. Then getting the log likelihood of this is the only part which will remain as the log, and the log of an exponential. So remember the exponential function is an inverse of the logarithmic function. So meaning if I get the natural, or ln basically, it is a log base e. L is a natural logarithm, meaning it is a log base e. So when I find the log base e of an exponential variable, this exponential disappears, and that is why I remain with this part as 1 over 2 sigma squared, the summation from I is equals to 1 to n xi minus mu squared. Now, these are the part here, the way we are obtaining these are the part that we have here. It is from getting the log of this. So the log of 2 pi sigma squared raised to power negative n over 2 is the same as I multiply by negative n over 2, and I get the log of 2 pi sigma squared. So multiplied by negative n over 2, I get the log of 2 pi sigma squared. Now, it is see? Which will give me negative n over 2 log 2 pi, negative n over 2 log 2 pi minus the n, the log of sigma, because this is again sigma squared here. This is sigma squared. All the three is just illustrate this. This is a sigma squared, and this, all this is still under the negative. So it is the negative log of this. Now, when I split the two now, I'll get this to be negative n over 2, the log of 2 pi plus, because I'm splitting based on the logarithm. E log wacha niandike as the natural logarithm, not as log, but as ln. To write this as ln, this also as ln, is ln, plus the ln of sigma squared. That is when I separate based on that. The n over 2 is again still cutting across the two cases and the negative. So opening, I'll have the negative n over 2 ln of 2 pi, and this again, the 2 will come back to this case so that I have a minus because of this particular negative here. So I'll have minus 2 minus 2 multiplied by n over 2 ln of sigma, so that these 2 and 2 cancels, so that I have negative n over 2 ln 2 pi minus n ln sigma. N ln sigma. And that is how this part is coming out of this particular case. So that now I have that to be the log likelihood function. And normally this is actually what is implemented in R. So basically in R, when we use the log over function in R, when you use the log function in R, it means the natural logarithm of that. So meaning you needed to now involve some actual values, xi's. You'll just define that to be, define that particular values xi's, define your parameters, and just fix the same function, but using now ln. As you write ln, you write the log of that. Then let me show this other one. Second one might be a little bit simpler. Yes, using a Poisson distribution, we assume that xi all the way to xn values is a random sample from a Poisson distribution. The parameter theta. Theta, of course, is greater than 0 for a Poisson distribution. So the likelihood function L theta given x will be equals to the product sum from I is equals to 1 to n. And this is this is the distribution, the Poisson distribution. That is the theta raised to power x, because in place of lambda, I'm having now theta, then e raised to power negative theta divided by the x factorial. But now we are talking about the product sum. So several observations, xi's and xi parameter space. So this will give us that getting the product sum will give us e raised to power n theta, negative n theta for this case. Then the theta will be raised to power the summation of xi's, because these are the variance. So wherever we have the xi's observation, we'll get the summation of that. And since this is a factorial, we get the product sum of xi's factorial. Then we get the log of this. So the log of this, the e will disappear. Getting the log of this, the e will disappear and will be remaining with only negative n theta. Then plus, because it is a multiplication by this, so it is a plus the summation, the plus the ln theta, the summation of xi's. So of course, it should be the ln of theta raised to power the summation of xi's. So what will happen is that we'll have this to be the summation of xi's multiplied by ln theta. So these are based on the rules of logarithms. Whatever is a power can be multiplied, pre-multiplied with that. And that is why we have this multiplication by ln theta. Then whatever is in the denominator, we subtract the summation from I is equals to 1 to n, the log of the xi's factorial. And this gives us the log likelihood function for the Poisson distribution. So given any other distribution, we could easily get the log likelihood. Even if you're given a binomial distribution, you can get the log likelihood of the binomial distribution, the Bernoulli distribution, and any given distribution by only getting the product sum across that. Then you see how you simplify. Where we have the xi's, you put the summations, then you now get the log of that. That is the natural logarithm of that. Then this example should let's see this example here. M&M's sold in the United States have 50% red candies compared to 30% in those sold in Canada. In an experimental design, a sample of 5 candies were drawn from an unlabeled bag and 2 red candies were observed. It is more plausible that this bag was from the United States. Is it more plausible that this bag was from United States or from Canada? So it has 2 alternatives. It's either from the United States or it is from Canada, meaning the probability, meaning it is a two-way thing, which could maybe follow a Bernoulli kind of a probability. That is why this likelihood has been obtained based on the Bernoulli probability. So the likelihood function L theta given x has been given as theta squared 1 minus theta raised to power 3, with theta defined to be 0.3 or 0.5 based on where it is coming from. So taking our theta to be 0.3 given x, we apply this. So we'll have 0.3 squared into 1 minus 0.3 raised to power 3, which will give us this. And taking our theta to be equals to 0.5, meaning it is from the US. So for 0.3, it is from Canada. From 0.5, it is from the US. We take theta squared, which is 0.5 squared, into, so we are just taking a 0.5, we square that, and you multiply it by 1 minus 0.5 raised to power 3. And that is giving us a 0.3125. So when you make a comparison, we are seeing that this one is less than this, suggesting that it is more plausible that the bug used in the experiment is from the US, which is giving us a more probability. So more probability from US as compared to that from from Canada. So you could check these. This is some pretty fine. We could check some other distribution like Bernoulli and binomial and try to obtain the log likelihood of this. But you see how that comes about. Then also, yeah, we have the likelihood principle. If x and y are two sample points, such that the L theta given x is directly proportional to L theta given y for all parameters theta, then the conclusions drawn from x and y should be identical. Thus, the likelihood principle implies that the likelihood function can be used to compare the plausibility of various parameters. For example, if L theta 2 given x is equals to 2 L theta 1 given x, and L theta given x is directly proportional to L theta given y for all theta, then L theta 2 given y should also be equals to 2 L theta 1 given y. If the two are directly, so these are an identity that you are giving as the likelihood principle. So therefore, whether we observed y or x, we should come up with a conclusion that theta 2 is twice plausible as compared to theta 1. And taking this example of a multinomial, n is equals to 6, theta, we have theta 1 and theta 2 and 1 minus 2 theta. So the following two samples are drawn from this distribution from the same likelihood. So what will happen is that we'll have 1, 3, we have an x which has the observations 1, 3, 2. So it is 6 combination. So, talking about the multinomial distribution, we'll have a 6 factorial, 1 factorial, 3 factorial, 2 factorial, based on whatever we have here as our observed values. Then we have theta raised to power 1, theta raised to power 3, and 1 minus 2 theta raised to power 2, which is this. And also the other one is given by x222. These are the observed values. So 6 factorial divided by, because our n is 6, 2 factorial multiplied by 2 factorial multiplied by 2 factorial. Then the first theta parameter is raised to power 2, the second one raised to power 2. Then 1 minus 2 theta, we square that also. So this means that both samples should lead to the same conclusion regarding the relative plausibility of the different values of theta. So that is for the likelihood functions. Now I'll begin here with the Bayesian framework now. Once you're able to compute our likelihood function, how do you now move with the Bayesian rule or the Bayesian law, so that now we get the Bayesian distribution? And we'll define all these, the conjugate priors of each and every function, then do some derivatives now, complete derivations of better binomial Bayesian models. So let me look at this particular part and also those derivatives when we meet physically in the next class. So up to that point, not sure. Do we have anyone with a question? Anyone with a question? Eliud Yuko? Did we have Eliud around? Sijui kama ni mimi sijakusikia. Nimeona ni kama there's someone who unmuted. Eliud, any question? Didn't hear that. Mark, naona Mark yuko. Mark, any question? T24 ni nani? Okay, Dennis. Okay, Siombua.
I don't have any question.
Siombua, any question?
No, I don't have any.
Kama nimekusikia kwa umbali umesema no. Farin yuko? Farin,
Yes.
any question?
No, I'm okay.
Okay. Then who is left? 1074. 1074 ni nani? Maxon yuko? I know Meat is not around. 1074?
No question.
Oh, 1074 is the same person. Yeah, he joined twice. That is Elliot.
Yes, I've joined twice.
Oh, okay, so we have Eliud, Mark, Farin, Dennis, and Siombua. Okay, thank you for attending the class. I'm going to share